STM32 timers are extremely flexible, but that flexibility comes at the cost of complexity, especially when you're constantly recalculating PSC, ARR, and CCR values across different timers. In this video, I'm introducing a generic PWM abstraction layer for STM32 that automatically computes prescaler and auto-reload values, supports both 16-bit and 32-bit timers, and safely updates duty cycle and frequency at runtime. We'll walk through the implementation line by line, then validate the results on an oscilloscope with clean, stable PWM output. The library is available to download, but you'll need to watch through the video to get the link. Okay, let's begin. First, open STM32 IDE. Once it's open, go to the top menu bar, click File, then New, and select STM32 Project. Now we need to choose the target device. Since I'm working with the STM32 F407VGT6, I'll type STM32 F47VT6 into the search box. Select it from the list, click Next. Now give the project a name. I'll call mine PWM_STM32 F407VT6. When that's done, click Finish. You're now looking at the STM32 graphical configurator. This is where we configure GPIO, clocks, timers, and the core system. On the left-hand side, click System Core, then click Sys. Set debug to serial wire. Leave time base set to SysTick. Next, still on the left, click RCC. My hardware uses a high-speed external crystal, so I'll set high-speed clock to crystal ceramic resonator. I don't have a low-speed crystal fitted, so I'll leave low-speed clock disabled. Now we choose a pin for the PWM output. I'm going to use PB6 because that's where my oscilloscope is connected. Click PB6, select TIM4, then choose channel 1. You'll notice the pin turns yellow. That's expected. It means the timer isn't enabled yet. Before enabling the timer, we need to configure the system clock. At the top, click Clock Configuration. Set HSE input to 8 because my board uses an 8 MHz crystal. Find HCLK. I want the system running at 168 MHz. Type 168, press Enter. Click OK. Now return to the top and click Pinout and Configuration. On the left, expand Timers. Since we're using timer 4, click TIM4. The library we'll write later handles the complex setup automatically. Here we just need to define the basics. Set clock source to internal clock. Under channel 1, select PWM generation. This enables the PWM output on PB6, and that's it. Go to File, click Save. QBuddy will now generate the project. Now we move on to the next big step. We need to write the library. This is what makes our code easier to use, easier to maintain, and easier to scale. And this is the correct way to do it. We're going to create two separate files. The first file is called plib.h. This will be our header file. The second file is called plib.c. This will be our implementation file. Before we write a single line of code, we make sure the foundation is in place. Look to the left-hand side. In System Explorer, expand the project. Then expand Core. Inside Core, you'll see two folders, INC and SAR-C. This structure matters. Header files live in INC, source files live in SAR-C. So let's start with the header. Right-click on it, choose New. Select Header File. Name it pwmlib.h. Click Finish. CubeIDE now generates the header file. Before touching it, we create the implementation file. Right-click on SRC, choose New, select Source File, name it pwmlib.c, click Finish. CubeIDE generates the source file. Before closing it, go to the very top of pwmlib.c and include the header file. This connects the implementation to the interface. Now in Project Explorer, right-click the project itself and click Build. Once the build completes, return to the header file, pwmlib.h. This next step is optional, but I always do it. I remove unnecessary whitespace, cleaner files, clearer structure. What CubeIDE generated here is called an include guard, also known as a header guard. This is a small block of preprocessor code that prevents the header file from being included more than once during compilation. Here's what that means. The first time the header is included, a unique macro is defined. If the same header is included again, the compiler sees that macro is already defined, and it skips the contents of the file. This prevents duplicate definitions, linker errors, and subtle build issues. Next, I always add my own guard, extern C. Extern C allows C code to work correctly with C++. By default, C++ changes function names internally. This is called name mangling. C does not do this. Without extern C, the linker would fail to match C functions when the header is included in a C++ project. The ifdef C++ guard ensures this code is only seen by a C++ compiler. A C compiler safely ignores it. This allows the same header file to work perfectly in both C and C++ projects. Clean, correct, professional. Now the foundation is set, and we're ready to write the PWM library. I always start by writing the header file first. This defines the public face of our library. It tells the rest of the project what exists, what's available, and how to use it. The first thing we do is include the required C and C++ header files. These expose the core functionality we'll be working with. We start with STM32 F4XX_HAL.h. This pulls in the STM32 HAL driver definitions, giving us access to STM32 peripherals, hardware registers, and HAL functions for things like timers, GPIO, and clocks. Next, we include stdint.h. This provides standard fixed-width integer types such as uint8, uint16, and uint32. These guarantee consistent integer sizes across all platforms and all compilers. With the includes in place, we define our core data structure. This is a struct. The struct defines a custom data type called PWM device. This single structure holds everything required to control one PWM output. It stores a pointer to the STM32 timer handle, it stores the timer channel being used, it stores the current prescaler value, and it stores the user-defined PWM settings such as frequency and duty cycle. By grouping all of this together, we can manage configuration, state, and control through one clean interface. One device, one structure, no mess. Next, we define the function prototypes. These are declarations only. The actual implementation will live in the C source file. Function prototypes tell the compiler what functions exist, what they are called, what parameters they accept, and what they return. They do not contain code. This allows the compiler to recognize functions before they are used. It allows multiple source files to call the same functions, and most importantly, it defines the public API of the library. The header exposes what other code is allowed to use, while the C file hides how it actually works. Clean separation, clear intent, professional structure, and with that, the header file is complete and the PWM library is ready to take shape. Now let's build the project. Right-click the project and choose Build. It looks like we've got an error. No panic. Looking closer, there it is. I've spelled float wrong. Easy fix. Correct the spelling and build again. Perfect. This time, the project builds cleanly with no errors, exactly what we want. Now we reach the meaty part. This is where we write the implementation code for the functions we defined earlier in the header file. This is where everything comes to life. I'm going to write one function at a time. As I type, I'll briefly explain what each function is doing and why it exists. Let's start with the initialize function. This function sets up a PWM output on an STM32 timer in a clean, step-by-step way. First, it stores all the user-provided settings. That includes which timer to use, which channel to use, the desired frequency, and the duty cycle. All of this information is stored inside the PWM device structure. This means the configuration is remembered, tracked, and easy to reuse later. Next, the function calculates the correct timer values needed to generate the requested PWM frequency. It does this by calling PWM_compute prescaler. This function works out the correct prescaler and the correct auto-reload register value. Once calculated, those values are written directly into the timer's hardware registers. After that, a timer update event is forced. This ensures the new settings take effect immediately. Finally, the function applies the requested duty cycle. It does this by calling PWM_setDC. This sets how long the PWM signal stays high during each period. And just like that, the timer is configured, the frequency is correct, the duty cycle is applied, and the PWM output is up and running. Clean, predictable, powerful. Now let's build the project. Right-click the project and select Build. There's a warning. Looking closer, I see it. I wrote PWM_compute, but what I actually meant was PWM_compute prescaler. Easy fix. Correct the function name and build the project again. Perfect. No warnings, no errors. Exactly how it should be. Now let's move on to the next function. Once again, as I type, I'll explain exactly what it's doing. This function is used to change the PWM frequency after the output has already been set up and running, and it does this in a safe and controlled way. First, the function checks the requested frequency. If the value is too low, it forces it to be at least 1 Hz. This prevents invalid values and avoids unstable timer configurations. Next, it calculates the new timer values required to generate that frequency. Specifically, it works out the correct prescaler and the correct auto-reload register value based on the timer's clock. Before applying these new values, the function stops the PWM output. This is critical. Stopping the output ensures the signal does not glitch, jump, or briefly produce an incorrect waveform while the timer is being reconfigured. Once the PWM is stopped, the function updates the PWM device structure. It stores the new frequency and the new prescaler, so the device state remains accurate. The calculated prescaler and auto-reload values are then written directly into the timer's hardware registers. An update event is forced, so the changes take effect immediately. Because changing the frequency also changes the timer period, the duty cycle must be handled carefully. So the function reapplies the existing duty cycle, recalculating the compare value to ensure the on-time percentage remains correct. At this point, the PWM is fully reconfigured at the new frequency, stable, accurate, predictable, and from here the PWM output can be restarted with confidence. Now we move on to the next function. Once again, as I type, I'll explain what it's doing. This function is responsible for setting the PWM duty cycle. The duty cycle controls how long the signal stays high during each PWM period. First, the function clamps the duty value. This ensures the duty cycle always stays within a valid range, from 0 to 100%. This prevents invalid settings that could break the timer logic or produce undefined behavior. Next, the function reads the timer's auto-reload register, also known as ARR. The ARR represents the total number of timer counts in one PWM period. We then add 1 because the timer counts from 0 up to ARR inclusive. Now comes the key calculation. The function converts the duty cycle percentage into a compare value, also called CCR. This value represents how much of the total period the output should remain on. That compare value is then written into the correct capture compare register. This could be CCR1, CCR2, CCR3, or CCR4, depending on which timer channel is being used. From here, the timer hardware takes over automatically. It uses the compare value to switch the PWM output on and off at exactly the right time during each cycle. Finally, the function stores the duty cycle value back into the PWM device structure. This ensures the current setting is remembered and can be reused later. Accurate, safe, fully under control. That's the duty cycle function. Clean, predictable, and reliable. Now we move on to the next function. Once again, as I type, I'll explain what's happening. This function reads back the current PWM duty cycle directly from the hardware timer and returns it as a percentage. First, the function reads the timer's auto-reload register, also known as ARR. This value represents the total length of one complete PWM period. We then add 1 because the timer counts from 0 up to ARR inclusive. Next, the function checks which timer channel is being used. Based on that channel, it reads the corresponding capture compare register, or CCR. This register contains the value that determines how long the PWM output stays high during each cycle. Now we convert this raw timer data into something meaningful. The compare value is divided by the total period, then multiplied by 100. This converts it into a clear, human-friendly percentage. The function then returns the actual duty cycle currently being generated by the timer hardware. No assumptions, no cached values. This is the real signal coming straight from the hardware, accurate, trustworthy, fully transparent. And that completes the duty cycle readback function. Now we move on to the next function. Once again, as I type, I'll explain exactly what it's doing. This function calculates the actual PWM frequency being produced by the timer hardware. Not what we asked for, but what the timer is truly generating. First, the function gets the timer's input clock frequency. This is the clock that drives the timer's counter under the hood. Next, it reads the timer's prescaler, also known as PSC, and the auto-reload register, or ARR. Together, these two values define how fast the timer counts. The function then calculates how many clock ticks make up one full PWM period. It does this by multiplying PSC plus 1 by ARR plus 1. That gives us the total number of timer clock cycles per PWM period. Finally, the function divides the timer clock frequency by this total number of ticks. The result is the real output frequency returned in hertz. This includes any rounding effects introduced by the hardware configuration. Exact, measured, hardware accurate. And that completes the function that tells us what frequency the PWM is actually running at. Now we move on to the next function. Once again, as I type, I'll explain exactly what's happening. This function determines the actual clock frequency feeding a specific STM32 timer. This step is critical. Without the correct timer clock, all PWM calculations would be wrong. First, the function checks which timer we're working with. If the timer is TIM1 or TIM8, it knows those timers are connected to the APB2 bus. All other general-purpose timers are connected to APB1. Based on that decision, the function reads the correct peripheral clock frequency using the STM32 HAL functions. Now comes an important STM32 detail. STM32 timers follow a special rule. If the APB bus is prescaled, meaning it's not running at full system speed, the timer clock automatically runs at twice the APB clock. So the function checks the RCC configuration register to see whether a prescaler is in use. If it is, the clock frequency is multiplied by 2. Finally, the function returns the correct timer clock frequency. This value is later used to calculate accurate PWM prescaler and period values. Precise, reliable, hardware aware. And that completes the function that tells us exactly how fast our timer is really running. Now we move on to the next function. Once again, as I type, I'll explain what it's doing. This function calculates the prescaler and the auto-reload register values needed to generate a requested PWM frequency on an STM32 timer. This is the core maths behind the entire PWM system. First, the function validates the requested frequency. If the value is too low, it forces it to be at least 1 Hz. This guarantees the calculations remain valid and nothing breaks. Next, the function determines the timer's base clock speed. It also checks whether the timer is 16-bit or 32-2-bit. This matters because it defines the maximum value the ARR register is allowed to hold. Now we calculate how many timer clock ticks are required for 1 full PWM period at the requested frequency. To do this, the function uses a simple but reliable brute force approach. It starts with a prescaler value of 0 and loops upward. For each prescaler value, it calculates the corresponding ARR value and checks whether it fits within the timer's limits. The moment a valid combination is found, that pair of values is stored as the best solution. The search then stops. A safety fallback is included just in case no valid combination can be found. Finally, the selected prescaler and auto-reload values are written back through the output pointers. These values can then be loaded directly into the timer registers to generate an accurate PWM signal at the desired frequency. Deterministic, robust, hardware-aware, and that completes the function that makes frequency control possible. Before we move on to the next couple of small helper functions, it's a good idea to build the project and fix any issues that might appear. So let's build it. I can see 2 warnings, no problem. Let's walk through them. The first warning says ARR is unused. This comes from the function PWM_getTIMDC. Inside this function, we calculate ARR, but we never actually return it or use it. That's why GCC raises the warning. Now, the second warning, it says best PSC set but not used. This one comes from PWM_compute PSC ARR. In this function, we calculate best prescaler and best auto-reload, but we never write those values back to PSC_out and R_out. Since the results are never used, the compiler treats the calculations as pointless and warns us. So let's fix both issues. We return the values properly, clean up the logic, and remove the warnings. Just follow me. Now let's build again. This time, a clean build. No warnings, no errors. Perfect. Now we write the final 3 helper functions. Once again, as I type, I'll explain what each one does. Let's start with the first helper function. PWM_ is 32-bit timer. This function checks whether the given timer is one of the STM32's 32-bit timers, specifically TIM2 or TIM5. These timers can count much higher than the standard 16-bit timers, and that matters when we're calculating how large a PWM period is allowed to be. The function is simple. It returns 1 or true if the timer is 32-bit, and it returns 0 or false for all other timers. Next, we have PWM_start and PWM_stop. These are clean, simple wrapper functions around the STM32 HAL. Internally, they call HAL_TIM_PWM_start and HAL_TIM_PWM_stop. All they do is start or stop PWM output on a specific timer channel. But the benefit is huge. The application code stays clean and all PWM control logic lives in one place, inside the PWM library. Simple, readable, well-structured. And with these final helpers in place, the PWM library is complete. Just before we write a simple test script, if you're still here, I want to say a massive thank you. It genuinely means a lot. If you found this useful, please like, share, and subscribe. It costs you nothing, but it helps me more than you know. Also on the screen right now, you'll see the download link. That's where you can grab the full PWM library source files and follow along at your own pace. All right. Let's move on to the test script. I'm now going to flash this project directly to my board using CAN bus with CAN Flash Studio. To do that, I need to quickly configure this project so it's compatible with my CAN bootloader setup. This includes enabling the required CAN settings, making sure the memory layout is correct, and confirming the firmware is built in the right format for flashing over CAN. I'm not going to walk through those steps again here. I've already created a full in-depth video that covers this process from start to finish. If you haven't watched it yet, you'll find it right here on my channel. Once that setup is complete, I'll use CAN Flash Studio to detect the node and flash the firmware straight over the CAN bus. All right, let's get this tested. Open up main.c. At the top of the file under User Code Begin include the PWM library header file. Next, scroll down to User Code Begin 0. Here define the PWM device object. Now scroll further down into the int main function. After HAL initialization, inside the User Code Begin 2 section, add the PWM initialize call. Remember, I'm using timer 4 channel 1, but you can use any timer. That's the beauty of this library. Quick note before we continue. My oscilloscope is fairly low end, and the probes aren't great either, so the measurements may not be laboratory accurate, but they're more than close enough for this demonstration. First test. I'll initialize the PWM with a 1 kHz frequency and a 50% duty cycle. Last step, start the PWM. Now look at the scope. As you can see from the trace, it works, and the measurements match exactly what we programmed. Let's change it up. Next test, 200 Hz and 20% duty cycle. Back to the scope. Once again, the signal is correct and the measurements match what we set in code. One final test, this time 2 kHz and 65% duty cycle. And there it is, clean waveform, correct frequency, correct duty cycle, exactly as expected. And with that, I think that's a wrap. I really hope you found this useful. If you did, please don't forget to like and subscribe. Thanks for watching, and I'll see you in the next one.